Welcome to True Projects. In this video, we are going to explain about the project, which is malignancy detection in lung and colon histopathology images using transfer learning with class selective image processing. So first, we will know what is the project about. Malignancy in lung and colon histopathology refers to the presence of cancerous cells or tissues in the examined samples. These malignancies can manifest as abnormal cell growth, tissue architecture alterations, or the presence of specific cellular markers indicative of cancer. Accurate detection of malignancies in lung and colon histopathology images is crucial for early diagnosis and effective treatment planning in patients with lung and colon cancers. The project's focus is to develop an automated system for the detection of malignancies in lung and colon histopathology images. This system leverages the power of transfer learning and class selective image processing techniques to enhance the accuracy and efficiency of the detection. Traditional image processing techniques may not effectively capture the subtle features indicative of malignancies in histopathology images. Class selective image processing methods focus on extracting features specific to different classes to improve detection accuracy. Transfer learning involves leveraging pre-trained deep learning models trained on large datasets for a specific task and fine-tuning them for a related task with a smaller dataset. In this project, transfer learning will be applied to adapt pre-trained model to the specific characteristics of the lung and colon histopathology images. Objective of the project is to develop an automated system aimed at detecting malignancies in lung and colon histopathology images with the ultimate goal of enhancing early diagnosis and treatment efficiency for patients afflicted with lung and colon cancers. The aim is to utilize cutting-edge deep learning architectures such as AlexNet, VGG16, and MobileNet to extract features and classify histopathology images, thereby improving the accuracy and reliability of malignancy detection. The aim is to create a comprehensive automated system that is capable of accurately categorizing histopathology images into different types of malignancies, including adenocarcinoma and squamous cell carcinoma in both lung and colon tissues, while also distinguishing them from non-malignant tissue. This will facilitate precise diagnosis and treatment planning for patients with lung and colon cancers. Performance evaluation will be conducted through the comparison of implemented algorithms using standard evaluation metrics, which are accuracy, precision, recall, and FN score. This analysis will provide insights into the effectiveness of different models in accurately detecting malignancies and minimizing false positives and false negatives. The project aims to benefit healthcare professionals, including pathologists and oncologists, by reducing time and effort required for manual analysis of histopathology images. Additionally, patients with lung and colon cancers will benefit from earlier and more accurate diagnosis, leading to improved treatment planning and outcomes. Furthermore, advancements in automated diagnostic tools for cancer detection may benefit the broader medical community. To implement this project, we need software and hardware requirements. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, backend framework of Jupyter Notebook, database of SQLite 3. Front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. Coming to hardware requirements, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. To implement this project, we have designed various steps in the flow of work. So coming to the first step, which is importing the packages. In this step, necessary Python libraries are imported into the project environment. Here we have imported NumPy and Pandas for data manipulation, Seaborn and Matplotlib for visualization, sklearn for machine learning, Flask for web development, and TensorFlow for deep learning. The next step is importing the dataset. The dataset containing of lung and colon histopathology images along with their corresponding labels is imported into the project. This dataset serves as a foundation for training and testing the model. Coming to the next step, which is image processing. The imported images undergo pre-processing using image data generator class, which performs various transformations such as rescaling, resizing, and augmentation. Pre-processing prepares the images for feeding into the deep learning model. Coming to the next step, which is splitting the data into train and test. The dataset is split into two subsets. One is training set and the other one is test set. The training set is used to train deep learning model, while the test set is used to evaluate the performance and generalization ability. Coming to the next step, which is building the model. Here, transfer learning model architecture is defined and constructed in this step. This step typically involves selecting appropriate layers, specifying activation functions, and configuring model parameters. The next step is training the model. The constructed model is trained using the training dataset. During training, the model learns to map input features, input images to their corresponding labels through iterative optimization of its parameter using techniques such as gradient descent and backpropagation. The next step is Flask framework with SQLite for sign up and sign in. Flask, a lightweight web framework for Python, is integrated with SQLite, which is a relational database management system, to implement user sign up and sign in functionalities. This allows users to create accounts and authenticate themselves before accessing the prediction system. The next step is user gives input. In this step, user provide input to the system typically in the form of uploading histopathology images for malignancy prediction. The next step is given input is pre-processed for prediction. The input images undergo pre-processing similar to training data pre-processing step. This ensures that the images are properly formatted and transformed for compatibility with the trained deep learning model. The next step is trained model is used for prediction. The pre-processed input images are passed through the trained deep learning, which is transfer learning model for the prediction. The model generates predictions based on learned patterns and features extracted from the input images. The last step is final outcome is displayed through the front end. The predictions generated by the model are displayed to the user through the front-end interface. This allows users to visualize the predicted malignancy types and the outcomes associated with uploaded histopathology images. Algorithms which are used for detecting malignancy in lung and colon histopathology images are AlexNet. AlexNet is a convolutional neural network architecture introduced in 2012. It comprises 8 layers, including 5 convolutional layers, followed by max pooling layers, and 3 fully connected layers. AlexNet gained prominence for its breakthrough performance in ImageNet large-scale visualization recognition challenge. In this project, AlexNet is utilized as a pre-trained model for transfer learning. Its pre-trained weights learned from a large dataset like ImageNet are leveraged to extract meaningful features from lung and colon histopathology images. These features are then used to train a custom classifier specifically for malignancy detection. The next algorithm is VGG16. It is a convolutional neural network architecture proposed by Visual Geometry Group at the University of Oxford in 2014. It consists of 16 weight layers, including 13 convolutional layers and 3 fully connected layers with small 3 by 3 convolution filters. VGG16 is known for its simplicity and uniform architecture. VGG16 serves as a pre-trained model for transfer learning in this project. Its pre-trained weights, trained on large-scale images, are utilized to extract high-level features from histopathology images. These features are then utilized to fine-tune the model for improved malignancy detection accuracy. MobileNet. MobileNet is a lightweight convolutional neural network architecture developed by Google in 2017. It is designed specifically for mobile and embedded vision applications, featuring depth-wise separable convolutions to reduce computational complexity while maintaining high performance. MobileNet is employed as a pre-trained model in this project. Its lightweight architecture makes it suitable for deployment on resource-constrained platforms. By leveraging MobileNet's pre-trained weights, the project aims to efficiently extract relevant features from histopathology images for improved malignancy detection. We have used performance metrics which are accuracy, precision, recall, and FN score to evaluate all the models built in the project. So here we have performance comparison graphs for all these metrics. This is accuracy comparison graph where x-axis represents all the algorithm names and the y-axis represents accuracy score of each algorithm. Similarly, we will have for other graphs also. First, we will know what is accuracy. It is a proportion of correct predictions in a classification task measuring the overall correctness of a model's predictions. This is precision score comparison graph. It is the ratio of true positive predictions to the total positive predictions, representing model's ability to correctly identify all relevant instances while minimizing false positives. This is recall comparison graph. Recall is also known as sensitivity or true positive rate. It is the ratio of true positives to the total actual positives, measuring a model's ability to capture all relevant instances without missing any. This is F1 score comparison graph. F1 score is the harmonic mean of precision and recall, offering a balanced measure that considers both false positives and false negatives, making it suitable for imbalanced datasets. The algorithm which performs well among all these metrics will be used for final prediction. So here among the all algorithms, MobileNet is performing well, so it is used for final prediction. To execute the project, first we have to open the code folder which contains source code files. So I'm opening the code folder. This is the code folder of the project, and this is the dataset folder in which we have all different 5 classes. We use all these folders, which is the dataset for training the algorithms. And this is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in HTML templates. This is the models folder in which we have algorithm information and that will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. This is the signup.db file. This file is a database file used to store the user information. And this is the samples folder which we use for testing it in the front end. Now we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we need to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. With this, current directory will change to the code folder's path. So here we can see that current directory is changed to the code folder's path. And here we need to type the command python space app.py to compile app.py file. And now click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port, unless configured differently. So this is the local host and this is the port. Now we need to copy this local link provided by the Flask framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project, which is developed using Flask framework. To execute, first we need to log in, so click on login. Here to sign in, we need to provide our username and the password. If we are new users, first we need to sign up. For that, click on sign up and enter all the registration details if we are registering newly. I have already registered and I have an account in it, so I'll directly sign in. For that, click on sign in and provide username and the password. So I'm giving my username and the password and now click on login. I have logged in successfully and I'm redirected to prediction page. Here we can see a choose file button. We need to click on that for uploading histopathology images of colon and lungs. So click on choose file. From the test cases folder, I'm going to upload the first image. Now click on open. Here we can see that image has been loaded. Now click on upload. Based on the uploaded histopathology image, we got the prediction as colon N detected. Colon N detected is identification of non-malignant tissue in colon histopathology images. It is a benign condition, which means that it is cancer-free. Now we will try uploading the other image. Click on try again. Click on choose file. This time we'll be uploading second image. Based on the provided image, we got the prediction as lung ACA detected. It is the recognition of adenocarcinoma in lung histopathology image. It is a prevalent type of lung cancer developing in the lung's air sac lining cells, which means that it is a malignant type and there is a lung cancer in the cells. Now click on try again for uploading other images. So click on choose file. This time we'll be uploading the third image. Here we got the prediction as lung ACA detected. Now we will try using the other image. So click on try again. Choose file. This time we'll be uploading the fourth image. Click on open and now click on upload. So here, based on the provided histopathology images, it has been detected as lung N. Lung N is the detection of non-malignant tissue in lung histopathology images. It is a benign condition which is non-malignant tissue, which means that there is no cancer in the lung cells. Now we will try uploading the other image and see what will be detected. This time going to upload fifth image. Click on open and now click on upload. Here we got the prediction as lung N detected. Now we will try uploading the other image. So click on try again. Click on choose file. We'll be uploading sixth image. Click on upload. Here we got the prediction as lung SCC detected. Lung SCC refers to squamous cell carcinoma in lung histopathology image. It is another common type of lung cancer originating in squamous cells lining the air, which means that lung cancer has been detected and it is a malignant condition. Click on try again for uploading some more images. Click on choose file. This time we'll upload the seventh image. Here we got the prediction as lung SCC detected as a previous image, which is squamous cell carcinoma in lung histopathology images. It is a malignant type. Click on try again for uploading some more images. I'm going to upload the eighth image. Here, based on the provided input, we got the prediction as colon ACA detected. It is a detection of adenocarcinoma in lung histopathology images. It is the most common type of colon cancer originating from glandular cells, which is a malignant condition. Now we will upload one more image. Click on try again. Choose file. I'm going to upload the last image. Click on open and now click on upload. Here we got the prediction as colon N detected. It is non-malignant condition where there is no cancer in the cells. Now we will upload a last image. Click on try again. Click on choose file. We'll be uploading the ninth image. Click on open and now click on upload. Here, based on the provided image, we got the prediction as colon ACA detected, which is a malignant condition, and there are cancer cells in it. Now click on log out. In this way, just by giving the histopathology images of lung and colon to the system, it will detect malignancy detected or not. So the conclusion of the project is the project has been successfully developed, achieving its objective of automating malignancy detection in lung and colon histopathology images. This achievement streamlines diagnosis process, enhancing early detection and treatment efficacy for patients with lung cancer and colon early detection. Treatment and efficacy for patients with lung and colon cancers. Among algorithms utilized, MobileNet demonstrated superior performance in terms of accuracy, efficiency, and scalability. Its lightweight architecture and efficient feature extraction capabilities made it particularly well suited for the task of malignancy detection in histopathology images. MobileNet is deployed in the Flash-based frontend of the project, providing users with a streamlined interface for uploading histopathology images and receiving predictions regarding malignancy types. Its efficient processing ensures quick responses and seamless user experience. The project holds promising future directions, including expanding its applicability to other cancer types beyond lung and colon, such as breast or prostate cancer. Additionally, integration with emerging technologies like augmented reality for enhanced visualization and interpretation of histopathology images could further advance diagnostic capabilities. Moreover, collaboration with healthcare institutions for real world validation and deployment of the automated system could lead to its widespread adoption, ultimately benefiting the larger population of cancer patients.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.